The silence of 235,000 pounds of tractive effort is heavy. But the invoice for that silence is heavier. For 6 months, this Baldwin-Lima-Hamilton diesel locomotive sat motionless in the transfer yard, a massive, cold monument to lost revenue. In the logistics business, a machine that doesn't move is a liability that bleeds capital. At a rate of $5,000 per hour in lost port operations, compounded by accumulating demurrage charges and strict contractual penalties for delayed cargo, the downtime bill had already eclipsed $800,000. The yard manager was desperate, having already cycled through 8 different repair shops. Each crew arrived with the same modern confidence, and each departed with the same excuse. They failed because they brought laptops to a gunfight. They tried to plug diagnostic scanners into a machine built before the invention of the microchip, searching for error codes that didn't exist. The machine wasn't dead. It was simply waiting for someone who spoke its language. To understand why 8 commercial shops failed, you have to understand the Hamilton T89SA engine. This is not the sanitized, plastic-covered power plant found in a modern freight truck. It is an 8-cylinder, turbocharged inline diesel that breathes differently than anything built in the last 40 years. When you stand next to it, even when it is cold, you feel the density of the engineering. The smell is distinct, a mixture of sulfur, old distinct diesel oil, and the sharp scent of cold iron that has absorbed decades of industrial labor. The frame itself is a one-piece fabrication, a rigid spine designed to handle the violent forces of shunting heavy freight cars. This specific unit was not a museum piece preserved for Sunday excursions. It was a working transfer unit, a critical link in the supply chain responsible for moving megatons of freight from the dock to the main line. Its failure didn't just mean a quiet engine. It meant a logistical catastrophe that rippled through the entire port schedule. The previous technicians looked at the exterior rust and assumed the technology was primitive. That was their first mistake. The engineering inside a 1950s Baldwin is deceptively complex. The pressure-charged intercooling system was the first of its kind in a U.S. locomotive, a technological leap designed to force dense, cool air into the cylinders to maximize combustion efficiency. It relies on a precise balance of pneumatic pressure and mechanical timing that doesn't degrade gracefully. The disconnect between modern expectations and vintage reality is where the restoration money is usually lost. The modern technician is trained to look for an OBD2 port, a digital interface where the machine confesses its sins in alphanumeric codes. They are trained to replace modules, not to diagnose systems. But this machine operates on relay logic and pneumatics. There is no computer to tell you which sensor failed, because there are no sensors. There is only a complex network of copper contacts, air valves, and mechanical linkages. The brain of the locomotive isn't a silicon chip. It is a complex electro-pneumatic system anchored by a 162-point faceplate resistor ladder. This isn't software. It is a cabinet full of heavy-duty relays that physically snap open and shut, controlling the flow of high-amperage electricity to the traction motors. When you approach a machine like this, you have to abandon the mindset of a parts changer. You cannot simply order a replacement module from a catalog. You have to become a specialist in industrial archaeology. You have to look for the mechanical truth hidden in the wear patterns of the metal. The specialist doesn't look for a screen. They look for the physical evidence of operation. They trace the hydraulic lines of the governor, feeling for the viscosity of the oil. They inspect the silver contacts on the relays for the telltale pitting of electrical arcing. They understand that the machine is a closed system of pressure and resistance. The previous crews saw a broken engine. The specialist sees a system that has lost its equilibrium. They saw a lack of fuel pressure. The specialist sees a governor that isn't communicating with the fuel rack. This distinction is critical. The modern diagnostic approach isolates components: the pump, the injector, the filter. The institutional approach views the machine as a living organism, where a pneumatic leak in the control stand causes a fuel starvation symptom in the engine. The T89SA is a beast that demands respect, and it offers no clues to those who do not understand its anatomy. The 8 shops that failed were looking for a digital signal in an analog world. They were trying to read the software when they should have been reading the hardware. But before we could even touch the engine, we had to understand the crime scene left by the others. We had to audit the incompetence that had turned a manageable repair into an $800,000 disaster. The machine was telling a story of neglect, but the service records told a story of professional malpractice. The service history for this locomotive was not a repair log. It was a confession of ignorance bound in a 3-ring binder. Before touching a single bolt on the machine, we had to review the paper trail left by the previous 8 shops. It was a thick, disorganized stack of invoices that detailed a systematic assault on the client's bank account. This is what we call the parts cannon approach in the industry. When a technician does not understand the root cause of a failure, they simply load a cannon with expensive components and fire it at the machine, hoping something sticks. In this case, the folder documented a frantic attempt to buy a solution that could only be earned through diagnosis. The pages were filled with high-dollar line items, turbochargers, fuel pumps, actuator motors, that had been replaced not because they were tested and found defective, but because the technicians had run out of ideas. This goes beyond simple incompetence. It borders on professional malice. Professional malice is the act of replacing a functional, original component with a new, inferior aftermarket part, simply to generate billing hours and the illusion of progress. The invoices showed that the previous crews had replaced the original Hamilton turbocharger, a component built with the durability of a tank turret, with a remanufactured unit that likely had looser tolerances than the original. They had pulled the fuel injectors, claiming they were clogged, and installed a new set that cost $12,000. Yet, the engine still refused to carry a load. They had even pulled a traction motor for a rewind, a massive operation that likely cost $20,000 alone, based on a diagnosis that was almost certainly a misinterpretation of a ground fault. They were performing invasive surgery on a patient that only needed a chiropractic adjustment. The driving force behind this waste was the phenomenon of ghost codes. In a modern machine, a computer monitors resistance and voltage. If a value drifts, it throws a code. The technicians working on this Baldwin were accustomed to that binary feedback loop. When they applied their multimeters to the 1950 circuitry, they saw resistance values that looked wrong to eyes trained on 2020's automotive standards. They saw phantom resistance caused by oxidized chassis grounds and hallucinated electrical faults. They didn't understand the baseline. They interpreted the floating voltage from a compromised return path as a short circuit. They were chasing ghosts, dismantling the locomotive's nervous system to find faults that existed only in the corrosion they failed to inspect. The financial toll of this guesswork was staggering. The invoices totaled $58,000 in parts and labor. That is $58,000 spent to make the machine arguably worse than it was when it failed. This figure does not include the $800,000 in lost port operations. This was just the cost of the insult added to the injury. The client had paid the price of a luxury car for a pile of scrap metal and a locomotive that still wouldn't move. It is a systemic failure in the modern repair industry. The business model encourages swapping components until the symptoms disappear, rather than diagnosing the disease. It is a method that bankrupts clients and disrespects the mechanical integrity of the machine. The most egregious evidence of this incompetence was found in the wiring harness. One of the invoices proudly listed a complete electrical modernization of the governor control circuit. When we inspected the work, the reality was horrifying. The original, heavy-gauge, cloth-wrapped wiring, designed to carry significant amperage without heating, had been cut out. In its place, they had spliced in modern, thin-gauge automotive wire using plastic Deutsch connectors. These connectors are excellent for a sensor on a modern truck, but they are woefully inadequate for the heavy inductive loads of a 1950s locomotive solenoid. The upgrade had introduced a choke point in the electrical flow, creating resistance that generated heat rather than work. They had effectively tried to wire a house with headphone cables. This wasn't a repair, it was sabotage born of arrogance. They looked at the heavy, soldered terminals of the 1950s and saw them as obsolete, replacing them with plastic clips that would melt under the first real operational load. It was a fundamental misunderstanding of the physics involved. They assumed that because the technology was old, it was inferior. They didn't realize that the obsolete wiring was sized to handle the brutal reality of industrial current. We closed the binder. The invoices told us everything we needed to know about why the machine was still broken. It was time to stop reading the fiction written by the previous shops and start listening to the silence of the engine itself. Deep inside the high-voltage cabinet, shielded behind a heavy steel door that the previous crews had likely opened only to glance at with confusion, sits the true nervous system of the Baldwin-Lima-Hamilton. It is not a microprocessor. It is a massive, semicircular faceplate resistor, a piece of electromechanical art that dictates the conversation between the diesel engine and the main generator. This is the device that translates the pneumatic pressure from the throttle into the electrical excitation that drives the train. It is a physical ladder of resistance, comprised of 162 distinct copper contact points. When the engineer pulls the throttle, a hydraulic vane motor sweeps a carbon brush arm across these contacts, stepping the resistance up or down with a mechanical certainty that modern digital potentiometers can never replicate. This component is the gatekeeper of power. It does not approximate the load. It physically commits the system to a specific amperage. But when we shone our inspection light onto the faceplate, the failure of the previous 8 shops became immediately, painfully obvious. They had been looking for a software glitch in a system that operates on friction and contact pressure. The copper segments, which should have shone with the dull, clean luster of a well-maintained penny, were black with oxidation and pitted from years of micro-arcing. To the uninitiated, it looked like simple age. To a specialist, it looked like an open circuit waiting to happen. The laptop mechanics had seen a dirty old part. We saw a resistor bank that was choking the generator's field excitation. This is where the phenomenon of ghosting manifests in an analog system. In a machine without a computer, a ghost code isn't a digital error. It is a physical lie told by electricity. When the wiper arm hits a contact point covered in carbon buildup or oxide, the resistance spikes instantaneously. The generator's field circuit sees this infinite resistance and collapses, cutting power to the traction motors to protect itself. The engine dies, or the load drops to zero. A modern diagnostic tool, plugged into a retrofitted sensor, would interpret this sudden loss of load as a generator failure or a fuel system malfunction. The scanner sees the result, the drop in power, but it is blind to the cause. It cannot see the microscopic layer of soot that momentarily broke the circuit. The previous crews had chased this ghost for 6 months. They replaced the fuel pump because the engine died under load. They condemned the generator because the power cut out. They spent tens of thousands of dollars replacing heavy iron components because a 60-year-old piece of copper had a dirty face. They failed to understand that 1950s copper oxidizes differently than modern alloys. It develops a hard, dielectric shell that doesn't just discolor the metal, it insulates it. You cannot simply spray it with a can of generic contact cleaner and walk away, which is exactly what the service records suggested they had done. You have to physically abrade the oxidation. You have to restore the surface profile so the brush makes contact with the metal, not the history. The durability of this design is legendary, but it is not infinite. The original engineers built this rheostat to survive the vibration of a rail yard, the heat of the engine room, and the constant cycling of the throttle. It is a robust mechanism, far superior to the fragile printed circuit boards that replaced it in later decades. However, its strength is also its vulnerability. Because it is so overbuilt, it continues to function even when neglected, masking its slow deterioration until it reaches a critical threshold. The fixes attempted by the other shops, bypassing relays, splicing wires, swapping pumps, were attempts to outsmart a system they didn't respect. They treated the resistor ladder as an obsolete relic, ignoring the fact that it was the only thing telling the generator what to do. We traced the continuity across the arc of the faceplate. At notch 4, the resistance should have been linear. Instead, our multimeter showed a jagged, erratic signal that jumped from 0 to infinity and back again. Every time the wiper hit a pitted contact, the locomotive's brain effectively had a stroke. The machine wasn't broken, it was stuttering. The impossible restoration wasn't about reinventing the wheel, it was about cleaning the ladder. But the resistor was just the symptom of a communication breakdown. We needed to find the disease, and that disease was hiding in the hydraulic logic of the governor itself. If the resistor ladder is the nervous system, the Woodward PG governor is the autonomic brainstem of the locomotive. Mounted on the accessory drive, it looks like a simple black casing, but inside, it is a mechanical computer of terrifying precision. It uses the viscosity of oil and the pressure of air to perform calculus in real time. It balances the engine speed against the load demand, adjusting the fuel rack with a sensitivity that rivals any modern digital control unit. But unlike a digital system that processes binary code, the Woodward processes physics. It relies on a complex interaction of rotating flyweights, hydraulic pilot valves, and pneumatic bellows. It is a device where a single grain of dirt can stop a 200-ton machine dead in its tracks. This governor was the source of the impossible problem that had baffled the previous 8 shops. The symptom was maddeningly consistent. The massive Hamilton T89 SA would fire up, finding its idle with a rhythmic, heavy chug. But the moment the engineer called for power, the moment the throttle was notched out to move a load, the engine would falter. It would gasp, stumble, and die, behaving exactly like an engine starved of fuel. It was a perfect mimic of a clogged filter or a failed lift pump. And that is exactly how the previous mechanics treated it. They saw a fuel starvation symptom and attacked the fuel system with their parts cannon. The invoice binder was filled with charges for new transfer pumps, rebuilt injectors, and enough fuel filters to stock a warehouse. They spent weeks bleeding lines and pressure testing rails, convinced that the diesel wasn't reaching the cylinders. They were wrong. The fuel was there, waiting at the inlet of the injectors. The problem was that the governor was refusing to let it in. In a diesel engine, the fuel rack determines how much fuel is injected. The governor moves that rack. If the governor decides the engine doesn't need fuel, the engine starves, no matter how new the pump is. The previous shops ignored the governor because they were afraid of it. To the uninitiated, a Woodward PG is a do-not-touch box. It is filled with springs under tension and valves with clearances measured in microns. Opening it without understanding the hydraulic logic inside is a recipe for disaster. But avoiding it was fatal to the restoration. We cracked the case and found the assembly line secret that the laptop generation had missed. The linkage connecting the pneumatic receiver to the pilot valve isn't something you set with a torque wrench or a laser. It requires a specific hand feel. You have to disconnect the return spring and move the linkage by hand, feeling for the hydraulic drag of the pilot valve plunger. It should move with the smooth, viscous resistance of the oil, not the gritty friction of metal on metal. If it binds even slightly, the governor hunts. If it's too loose, the engine overspeeds. The previous mechanics had tightened the linkage nuts to a standard torque spec, binding the pilot valve just enough to delay its reaction. The governor was lagging behind the engine, starving it of fuel every time the load changed rapidly. But the binding was only half the problem. The real killer was the calibration data itself. The previous shops had calibrated the governor, and they had done it correctly, according to Form 1000. Form 1000 is the generic Bible for Woodward governors. It lists the standard pressure settings for thousands of industrial applications. It tells you that at idle, the pneumatic signal should be 10 psi, and at full load, it should be 40. They set the governor to these numbers with digital precision. The problem is that a Baldwin-Lima-Hamilton T89 SA doesn't read Form 1000. It operates on a specific, forgotten dialect of engineering, documented only in Form 1200. The Hamilton engine requires a higher baseline pneumatic pressure to overcome the massive return springs on its fuel racks. By setting the governor to the standard generic specs, they had effectively lobotomized it. The governor was receiving the signal to accelerate, but the pneumatic pressure was too weak to push the pilot valve open against the internal resistance. It was trying to scream, "More fuel," but it could only whisper. The engine wasn't broken. It was being suffocated by a calibration that was mathematically perfect and mechanically wrong. We had the theory, but proving it required finding the lost blueprint. The search for the specific technical data did not happen on a computer screen. You cannot type Hamilton T89 SA governor transition logic into a search bar and expect a result. That information does not exist in the cloud. It exists in the physical world, buried in the stratification of history. We didn't look online. We went to the archives. This is a collection of steel filing cabinets weighing as much as the engine blocks they document, filled with paper that smells of mildew, oxidizing ink, and decaying binding glue. This is the Specialists' Library, a sanctuary of forgotten knowledge where the DNA of American industry is preserved on yellowing vellum. We were looking for a specific technical bulletin. The standard Woodward manual, the one the previous shops had likely downloaded for $20, covers the general operation of the PG governor. It is fine for a generic application, but useless for a locomotive with this specific transition control logic. We dug through the files for the Baldwin-Lima-Hamilton specific addendums. We were looking for a ghost in the paper trail, a document referenced in the footnotes of the footnotes. After hours of sifting through schematic folders and parts lists, we found it. It was a single, faded sheet of paper, stapled to the back of a 1951 Field Service update. The header read, Form 1200B and OTRRA-ST Addendum. This was the Rosetta Stone. The TRRA designation indicated a specification for the Terminal Railroad Association, a client that demanded aggressive switching performance. This addendum didn't just list pressure settings, it detailed a specific mechanical deviation from the standard assembly. It described the blueprint secret that had eluded 8 professional repair crews. The document specified a shimming requirement for the governor pilot valve radically different from the standard 0 lash setting. The text was explicit. It called for a negative lash, or a preload on the pilot valve spring, achieved by inserting a specific thickness of shim stock between the floating lever and the valve plunger. This was the missing variable. In the standard configuration, the valve opens explicitly when the flyweights move. In this high-performance configuration, the valve is preloaded to snap open the instant the pressure changes. It was a hair trigger modification designed to make the massive diesel engine respond like a sports car. This nuance is invisible to the eye, but essential for operation. The document also illuminated a lost manufacturing practice. It referenced blue-class shims. On the 1950 assembly line, workers didn't measure every valve with a micrometer. They relied on a color-coded system of pre-ground shims. A blue shim was exactly 12 thousandths of an inch thick. A red shim was 15. The workers knew by feel which shim to use to get the engine to breathe right. When the modern shops rebuilt the governor, they threw away these old spacers, thinking they were just wear washers. They replaced them with standard washers, erasing the engine's muscle memory. They deleted the physical programming that told the governor how to handle a heavy load. This is the critical difference between repairing a machine and restoring a capability. The previous shops had the general service manual, which told them how to assemble the parts. We had the build sheet, which told us how to tune the soul of the machine. They were working from a map of the forest. We had the coordinates of the specific tree. That single piece of paper, recovered from a damp basement archive, was worth more than the $58,000 in new parts currently bolted to the engine. It was the proof that the machine wasn't broken. It was simply misunderstood. The value of maintaining a physical library of technical data cannot be overstated. In an era where information is assumed to be free and instant, the real answers are often locked in analog formats. This archive is not a collection of nostalgia. It is a tactical asset. It is the only reason we can still service the infrastructure that built the world. We had found the instruction manual for the impossible. The logic was clear, the math checked out, and the mystery of the fuel starvation was solved on paper. Now, we had to transfer that truth from the page to the iron. We had the map. Now we had to perform the surgery. We put the laptops away. The repair of a Baldwin-Lima-Hamilton doesn't happen on a keyboard. It happens with a set of jeweler's files, a can of industrial contact cleaner, and a sheet of brass shim stock. This was analog surgery, requiring a steadiness of hand that modern diagnostics have made obsolete. We started with the faceplate resistor. The 162 copper contacts were not just dirty, they were scarred. The previous shops had likely sprayed them with solvent and walked away, but chemical cleaning doesn't remove the pitting caused by 50 years of high-voltage arcing. We had to physically resurface the latter. For 8 hours, the shop was silent except for the rhythmic sound of a fine-tooth file against copper. We treated each contact point like a piece of jewelry. You cannot rush this. If you take off too much material, you change the resistance value and ruin the calibration. If you take off too little, the carbon brush will skip and the ghost codes will return. We polished until the copper shone with a deep, uniform luster, checking the continuity of every single step with an analog multimeter. The needle sweep had to be smooth, without a single flicker or drop. When we finished, The resistance curve was a perfect, unbroken line. The nervous system was healed. Next came the chassis ground. We traced the main negative cable from the battery bank to the frame. It looked secure, bolted down with a heavy hex nut. But when we backed the nut off, we found the signature of a cosmetic restoration. The previous crew had painted the frame before reattaching the ground cable. They had bolted a copper terminal onto a layer of industrial enamel. Paint is an insulator. They had effectively floated the entire electrical system of the locomotive, relying on the threads of the bolt to carry hundreds of amps. It was a choke point that explained the erratic sensor readings and the burnt-out motors. We took a grinder to the frame, stripping the paint down to bare, bright steel. We applied conductive grease and bolted the cable back down. The resistance dropped from 4 ohms to 0.01. The ghosts evaporated instantly. Then we moved to the governor. This was the critical operation. We disassembled the pilot valve linkage, laying the parts out on a clean white rag. We cut a custom shim from brass stock, measuring it with a micrometer to match the Form 1200 specification of 12 thousandths of an inch. This tiny sliver of metal was the difference between a working engine and a paperweight. We installed the shim and reassembled the linkage. The adjustment process is not visual, it is tactile. You have to feel the hydraulic drag. We spent 6 hours adjusting the floating lever, tightening and loosening the jam nut by fractions of a degree. You are looking for a specific sensation. The valve plunger must float on the oil film. If you feel the metal of the plunger touch the wall of the bore, it is too tight. Friction is the enemy here. It took dozens of attempts, assembling and disassembling, until the movement was frictionless. We connected a manometer to the test port and manually stroked the linkage. The pressure gauge snapped to attention instantly, holding the higher Form 1200 baseline without a trimmer. Reinstalling the components felt less like repair and more like rearming a weapon. The governor bolted to the accessory drive with a solid thud. The control rods snapped into their ball joints with a distinct mechanical click, a sound of authority that had been missing. There was no play, no slop. We verified the rack travel one last time. It moved freely, springing back to the fuel-off position with a heavy, satisfying clack. The loose, vague feeling of the standard calibration was gone. The machine was tight. The surgery was successful, but the patient was still in a coma. We had restored the mechanical pathways, but until the crankshaft turned, it was all just theory. The climax of a 6-month failure isn't a shout, it's a vibration. The rail yard was dead quiet, save for the distant hum of the port cranes that were currently operating without this locomotive. The client stood by the track, arms crossed, watching with the exhausted cynicism of a man who had already paid for this performance 8 times before. He wasn't expecting a miracle. He was expecting another invoice for another failed attempt. The pressure in that silence was absolute. There were no more theories to debate, no more blueprints to discover. There was only the cold iron of the engine block and the physics of combustion. If the shim was wrong, or the resistor was still dirty, or the ground was still floating, the machine would remain an $800,000 paperweight. We climbed into the cab. The smell of ozone, old vinyl, and diesel fuel is the same in every locomotive built since 1950. It is the scent of potential energy. We closed the main battery knife switch. The heavy copper contacts engaged with a solid mechanical thud. The cab lights flickered to life, dim and yellow. Next came the fuel pump breaker. Deep in the bowels of the car body, the transfer pump began to whine, priming the system, pushing diesel against the fuel rack we had just calibrated. We let it run for a full minute, ensuring the air was purged, ensuring the pressure was building against the governor's pilot valve. Then, we pressed the start button. The Hamilton T89SA doesn't start like a modern engine. It doesn't just catch and run. It wakes up. The starter motors engaged, and the massive crankshaft began to turn. You could feel the reciprocating mass of the 8 cylinders fighting the compression. Whirr, clunk. Whirr, clunk. The rotation was slow, deliberate. Then, cylinder number 3 fired. Then 5. A puff of white smoke shot from the stack. unburnt fuel clearing its throat, and then the engine caught. It settled into its idle immediately. This is where you know if you are dealing with a healthy machine. A modern diesel hums. A Hamilton T89SA chugs. It has a rhythmic, percussive heartbeat, thump, hiss, that resonates through the floorboards. The idle was steady. The governor wasn't hunting. The needle on the oil pressure gauge climbed to 40 psi and stayed there, rock solid. The previous mechanics had achieved this part too. The engine would always idle. The lie was in the load. We let the temperature build. The water jacket needed to be warm. The oil needed to thin out. After 10 minutes, the moment of truth arrived. We released the independent brake. We threw the reverser handle forward. The contactors in the high-voltage cabinet snapped shut, a sound like a gunshot that tells you the electrical circuit is live. The client stepped back, watching the stack. We didn't ease into it. We pulled the throttle handle straight out to notch 8. This is the load test. In a modern machine, the computer would ramp the power instantly, but the manual for the T89SA is specific. Full speed and full power in approximately 20 seconds. We watched the second hand on the dash clock. 1 second. The governor solenoid energized. The pilot valve, now preloaded with our 12,000th shim, snapped open. There was no hesitation, no lag. 5 seconds. The pneumatic pressure hit the fuel rack. The engine note deepened, changing from a chug to a roar. The turbocharger began to spool, the whine rising in pitch as the intercooler did its job. 10 seconds. The wiper arm on the resistor ladder swept across the contacts we had filed by hand. It moved smoothly, finding clean copper. The ammeter needle began to climb. 500 amps, 600, 800. There was no arcing, no ghost codes. The generator accepted the command. 15 seconds. The floorboards were vibrating violently now. The engine was screaming, a mechanical symphony of 1,200 horsepower fighting against the traction motors. The locomotive lurched forward, taking up the slack in the couplers. 20 seconds. The needle hit the peg. Full load. The exhaust was clear. No black smoke, meaning the fuel-to-air ratio was perfect. The governor was holding the RPM exactly at the red line. The machine didn't just move, it surged. It pushed against the brakes of the test cars with the raw, unstoppable torque that built the American industrial base. We held it there, wide open, listening for a miss, a stumble, a drop in voltage. There was nothing. Just the deafening, beautiful roar of a system in equilibrium. We looked out the window. The client's arms were no longer crossed. He was staring at the exhaust stack, then at the wheels turning, his mouth slightly open. The cynicism had evaporated, replaced by the shock of seeing the dead rise. The ghost codes were gone. The impossible fuel starvation was gone. The machine was doing exactly what the blueprint said it would do in 1950. It was alive. Not because we bought a new computer, but because we listened to the old one. The bill was paid, but the lesson was free. The root cause of this $800,000 hemorrhage wasn't mechanical failure. It wasn't the age of the Baldwin-Lima-Hamilton, nor was the complexity of the pneumatic governor to blame. The real failure point was the industry's collective amnesia. We have built a technical culture that prioritizes replacement over understanding and speed over comprehension. The 8 shops that failed didn't fail because they lacked intelligence. They failed because they were products of a system that has forgotten how to think. They are trained to trust the screen, to obey the code, and to view the service manual as a set of rigid instructions rather than a philosophical guide to the machine's intent. When the screen stays dark, they are blind. This parts changer mentality is an expensive luxury in a world filled with legacy infrastructure. It assumes that every problem has a corresponding part number, and every solution comes in a cardboard box. But you cannot buy a solution for a machine like the T89SA. You have to manufacture it using the raw materials of patience and history. The invoices we audited prove that modern diagnostic training is often just a sophisticated form of guessing. They spent $58,000 proving that they didn't know how a resistor worked. They treated the symptoms with cash, hoping the problem would be bribed into submission. The reliance on digital diagnostics has created a workforce that is terrified of mechanical ambiguity. They see a linkage and want a sensor to tell them where it is. They see a wire and want a diagram on a tablet. When those crutches are removed, they panic. They start replacing things that look old, equating age with failure. This is not just bad mechanics, it is bad economics. This restoration proves that the most valuable tool in a heavy industrial shop is not the newest snap-on scanner or the most expensive oscilloscope. It is the library. It is the filing cabinet in the back room that holds the faded, yellowing paper of the original blueprints. A specialist, armed with a Form 1200 addendum, is worth infinitely more than a technician with a laptop and no context. Institutional knowledge is the only hedge against the obsolescence of our infrastructure. We live in a world built by these machines. Our power grid, our rail lines, our water systems, they run on the engineering of the mid-century. If we lose the ability to service them, we don't just lose a locomotive. We lose the capacity to maintain our own foundation. The cost of forgetting is not just the repair bill. It is the eventual failure of the systems that sustain us. We often hear that restoring these monuments is impossible, that the parts aren't available, the technology is too archaic, or the tolerances are too loose. That is a lie born of laziness. It was never impossible to fix this locomotive. The physics of 1950 haven't changed. The air pressure still moves the valve. The copper still carries the electron. The machine was screaming the solution the entire time. It was telling us about the ground fault through the heat, and about the governor through the idle. The computer couldn't hear it, so the mechanics stopped listening. The impossible restoration is usually just a routine repair that requires you to put down the digital tool and pick up a file. As we packed the tools, the yard was no longer silent. The deep, rhythmic thrum of the Hamilton engine had replaced the quiet of the financial loss. We left the Form 1200 document in the cab, tucked behind the sun visor. Maybe the next technician will find it before they order a new turbocharger. But more likely, they won't look. They will see an old, dirty machine and assume it is broken, unaware that the only thing broken is the way they are looking at it. The specialist leaves, not with a victory lap, but with the quiet satisfaction of knowing that for now, the machine is winning. The Baldwin-Lima-Hamilton leaned into the couplers, the exhaust heat distorting the air above the stack as it pulled the heavy freight without hesitation. 8 modern shops saw a broken computer and a dead engine. The specialist saw a miscalibrated governor and a dirty resistor ladder. If you respect the machinery that built the modern world and want to see the restorations that others refuse to touch, subscribe to the channel.